This is lecture number 7. This week we're going to finish talking about chapter 4. We'll talk about monotonic functions and the first derivative test, concavity and curve sketching, applied optimization, and antiderivatives. Section 4.6 is not included in this course. First, let's talk about monotonic functions and the first derivative test. Suppose that f is a continuous function defined on a closed interval, and let's suppose that f is differentiable on the open interval from a to b. If we know that the derivative of f is always positive, then we know that f is increasing on this closed interval. If we know that the first derivative is always negative, then we know that f is decreasing. For example, f of x be x cubed minus 12x minus 5. Find the critical points of f, that's the interior points of the domain where the derivative is either 0 or the derivative does not exist. And then part 2, identify the intervals where f is increasing and the intervals where f is decreasing. Now, f is a polynomial, and all polynomials are continuous everywhere and they're differentiable everywhere. So our domain is going to be the whole real line or any closed interval of the real line that we want. And there are no points where the derivative does not exist. So the only way that we can find a critical point is by finding places where the derivative of f is equal to 0. So we're looking for places where f prime of x is equal to 0. This is where we start. This function's easy to differentiate, and then we can factor to 3x minus 2x plus 2. How can we make this 0? This is 0 if x is minus 2 or if x is 2. So the critical points must be x is minus 2 and x equal to 2. Question 2, find the intervals where f is increasing and the intervals where f is decreasing. Well, remembering where we have our critical points, minus 2 and 2. We want to take our real line and I want to cut it at the critical point. So I'm going to make a cut at minus 2 and I'm going to make a cut at 2. After I've done these cuts, I have 3 open intervals. From minus infinity to minus 2, from minus 2 to 2, and then from 2 to infinity. We're going to look at the behavior on each of these new sub-intervals. We're going to calculate the derivative of f at one point in each interval, and then we're going to be able to see if f is always increasing on that interval or always decreasing on that interval. Because we know where the critical points are, we know that on each one of these intervals, f is always increasing or f is always decreasing. It can't go up, down, up, down, up, down inside one of these intervals because then we would have more critical points. So let's pick some number that's between minus infinity and minus 2 and calculate the derivative there. I'm picking the number minus 3 because minus 3 is between minus infinity and minus 2. And then I'm going to calculate the derivative of f. You can check later. This is equal to 15. 15 is a positive number, so the derivative must always be positive on this subinterval. And if the derivative is positive, that means the function must be increasing. Next, let's look at this middle interval between minus 2 and 2. The number 0 is between minus 2 and 2, and f prime at 0 is equal to minus 12. Again, you can check that later. Minus 12 is a negative number. That tells us that f prime is always negative between minus 2 and 2. So here the function is decreasing. And then finally, we're going to look between 2 and infinity. Calculate the derivative of f at one point, let's say calculated at 3, and we find a positive number. We don't need to know the exact number, we just need to know if this is positive or negative. Because there are no critical points between 2 and infinity, if the derivative is positive at one point, it must always be positive. So therefore, the function is increasing on this interval. So the conclusion is f is increasing on the interval from minus infinity to minus 2 and on the interval from 2 to infinity, and f is decreasing on the interval from minus 2 to 2. And I can show you a graph of this function. And we can see that if x is less than minus 2, the function is increasing. And then the function is decreasing between minus 2 and 2. And then it's increasing again after 2. That brings me to the first derivative test for local extrema. Suppose we have a continuous function defined on a closed interval. Let's suppose that C is a critical point f. And let's suppose that if we're close to C, not at C, but close to C, f is differentiable. So another way of saying that is if delta is a small number, we need that f is differentiable between C minus delta and C. It doesn't matter if f is differentiable or not at C. And we need that f is differentiable between C and C plus delta. F must be differentiable close to C, but we don't care what happens at C. And then we're going to look on the left of C, on the right of C, and then we're going to make a conclusion of what happens at C. First of all, let's suppose on the left of C, f prime is less than 0. That means the function is decreasing on the left of C. And let's suppose on the right of C, the function is increasing. F prime is greater than 0. So that's decreasing on the left of C and then increasing on the right of C. F must have a local minimum at C. Suppose we turn this upside down. We have a function which is increasing and then decreasing. Then we know that f has a local maximum at C. Or let's suppose we have a function which is increasing on the left of C and then it's increasing on the right of C. Then we don't have a minimum and we don't have a maximum. F does not have a local extremum at C. There's a typo here. This word is misspelled. And the fourth possibility is if the function is decreasing on the left of C and then it's also decreasing on the right of C, again, f does not have a local extremum at C. Have a look at this picture. First, let's look at C1. On the left of C1, the function is increasing, and on the right of C1, the function is increasing. We do not have an extremum here. What about at C2? It's increasing on the left and decreasing on the right. So we have a local maximum. At C3, it's decreasing on the left, and then it's increasing on the right. We must have a local minimum here, and so on. For example, let f of x be x to the power 1/3 multiplied by x minus 4. Or we can think of this as x to the power 4/3 minus 4x to the power 1/3. 1. Find the critical points of f. 2. Identify the intervals on which f is increasing and the intervals on which f is decreasing. And then 3. Find the extreme values of f. So what can we say about this function? Well, this function is continuous everywhere because x to the power 1/3 and x minus 4 are continuous functions. And we know continuous function multiplied by a continuous function is a continuous function. I want to calculate the derivative of f. I'm looking for the critical points of f. So I'm looking for points where the function f prime is equal to 0, and I'm looking for points where f prime does not exist. So differentiate this, we know how to do this, and then rearrange or simplify, however you want to think about this. We get 4x minus 1 over 3x to the power 2/3. Now we can't divide by 0. So we can say f prime does not exist if x is equal to 0. And we can see that f prime is equal to 0 if and only if x is equal to 1. So we have two critical points. One critical point where the derivative does not exist, and one critical point where the derivative is equal to 0. Using these critical points, we're going to cut up our real line. We start with the whole real line. We're going to make a cut at 0, and we're going to make a cut at 1. And that's going to give us 3 smaller intervals, 3 sub-intervals, between minus infinity and 0, between 0 and 1, and between 1 and infinity. And then we want to look to see if the function is increasing or decreasing on each one of these sub-intervals. So, for example, f prime of minus 1, you can check, is minus 8/3. This is a negative number, so f prime must always be negative on this interval. So f must be decreasing. Between 0 and 1, again, it's decreasing, and then between 1 and infinity, the function is increasing. So at 0, it's decreasing on the left and then decreasing on the right. We do not have an extremum here. At 1, it's decreasing and then it's increasing. So we must have a minimum, a local minimum at 1. We can see from this table that x equal to 1 is a local minimum and x equal to 0 is not an extremum. So the minimum value of f must be f of 1, and we can calculate that to whatever it is. There were no points where f had a local maximum, and because we're on an infinite domain, we don't have any endpoints. So f does not have an absolute maximum. The graph of the function looks like this. Okay, you can see we said it was decreasing between minus infinity and 0, decreasing between 0 and 1, and then it was increasing between 1 and infinity. We said that the derivative was equal to 0 when x is equal to 1. We can see that. And the derivative does not exist when x is equal to 0. Why? Because it has a vertical tangent just here. Another example. We're looking at the closed interval from 0 to 2 pi, and we're asked to find the critical points of sine squared x minus sine x minus 1. And then we're asked to identify the open intervals on which f is increasing and decreasing, and then find the function's local and absolute extreme values. So sine is a continuous function, sine is a differentiable function, so therefore sine squared x minus sine x minus 1 must be continuous on the whole closed interval, and it must be differentiable on our open interval from 0 to 2 pi. So there's no points where f prime does not exist. The only points where we can have a critical point, the only critical points are where 0 is equal to f prime of x. So I start with 0 is equal to f prime of x, and then I calculate that that is 2 sine x minus 1 multiplied by cos x. So this is 0 if and only if cos x is 0 or sine x is equal to a half. And remember, we are between 0 and 2 pi. So how can we have sine x is a half, or how can we have cos x is equal to 0? The only points where these can happen is pi over 6, 5 pi over 6, pi over 2, and 3 pi over 2. So we have our closed interval from 0 to 2 pi, and we're going to be cutting this. We have 4 critical points, so we're going to cut this at 4 places, and we'll end up with 5 sub-intervals. From 0 to pi over 6, pi over 6 to pi over 2, pi over 2 to 5 pi over 6, 5 pi over 6 to 3 pi over 2, and 3 pi over 2 to 2 pi. In each one of these intervals, we can pick some number and calculate f prime, and then look to see, is it positive or is it negative? Here, the function goes negative, positive, negative, positive, negative. So that's decreasing, then increasing, then decreasing, then increasing, then decreasing. The graph of the function actually looks like this. Decreasing, then increasing, decreasing, then increasing, then decreasing. If we want to calculate the extreme values, we calculate the value of the function at each one of these critical points and at the endpoints, and then we look to see which number is biggest and which number is smallest. And we're going to skip that part of the question. My second topic for this week, which is a lot longer topic, is about concavity and curve sketch. Have a look at this function. The red part of this function is increasing, and the green part of this function is also increasing. But their shapes are not the same. The red function is not just increasing, but it's curving upwards. The green function is increasing, but it's curving downwards. Why is that? It's because on the red part of the function, the second derivative is positive, whereas on the green part of the function, the second derivative is negative. When we have a graph which curves up like this, we say that the graph is concave up. When the graph curves down, like the green part of the function, we say it's concave down. We have the same idea on the orange and blue parts. Both orange and blue are decreasing, but their shapes are different. The orange part is curving downwards. It's because the second derivative here is negative. We say that f is concave down. Whereas the blue part of the function, here the second derivative is positive. The graph is curving upwards somehow. Here f is concave up. Let me give you the formal definition. Y is equal to f of x is concave up if f prime is increasing, and is concave down if f prime is decreasing. That's what that's the definition. That's what it strictly means. But you can think about the picture if you're trying to understand what is concave up and what is concave down. The second derivative test for concavity says, and this is repeating what I was saying when I was looking at the picture, if the second derivative is positive, then the function is concave up. If the second derivative is negative, then the function is concave down. So as long as we have a function which we can differentiate 2 times, for concavity, we're looking at the second derivative. Positive second derivative means concave up. Negative second derivative means concave down. For example, consider y is equal to x cubed. X cubed we can differentiate 2 times, and its second derivative is 6x. When is 6x equal to 0? When do we have y double prime equal to 0? Only if x is equal to 0. So we take our real line and we cut it at 0. So we end up with 2 sub-intervals between minus infinity and 0 and between 0 and infinity. And then we ask, is the second derivative positive or negative in each one of these? Between minus infinity and 0, 6x is negative. So here the graph is concave down. Between 0 and infinity, 6x is a positive. So here the graph is concave up. Another example. What about y is equal to x squared? Again, we can differentiate it 2 times, and then we can see the second derivative is always equal to 2. So the second derivative is always positive. That means y is equal to x squared is concave up everywhere. So let me repeat, y is equal to x cubed is concave down on the left and concave up on the right of 0. But x squared is concave up everywhere. Let me show you the graphs of these 2 functions. This is the graph of x cubed. As we saw, the graph is concave down on the left of 0 and is concave up on the right of 0. Whereas x squared we said was concave up everywhere. And yes, we can see decreasing and concave up on the left, whereas on the right is increasing and concave up. Determine the concavity of y is equal to 3 plus sine x on the closed interval between 0 and 2 pi. Well, first we need to differentiate this 2 times. The second derivative is minus sine x. How can we get this equal to 0 if we're between 0 and 2 pi? Well, only at pi, because sine of pi is equal to 0. So we make a cut at pi, and we split our interval into 2, an interval from 0 to pi, and another interval from pi to 2 pi. And then we ask, is the second derivative positive or negative on each one of these? Between 0 and pi, sine x is a positive number, so minus sine x must be a negative number. The graph y is equal to 3 plus sine x is concave down here. But between pi and 2 pi, the second derivative is positive, so the graph is concave up. I'm going to show you the graph of this function now. We're looking at the blue graph. The graph is concave up between 0 and pi, and then the graph is concave down between 0 and pi, and then between pi and 2 pi, the graph is concave up. That's because the second derivative is negative between 0 and pi, and the second derivative is positive between pi and 2 pi. Think back to critical points. Critical points were points where the first derivative didn't exist or the first derivative was equal to 0. And that was useful for us when we were trying to find places where the function changed from being increasing to decreasing or vice versa. For the second derivative, we have a similar idea. For concavity, we have a similar idea. If we have a point where the concavity changes, then it's called a point of inflection. But we need to be more careful than that. A point CF of C is called a point of inflection of y is equal to f of x if these two things are satisfied. First of all, the graph must have a tangent line, so nothing crazy going on there. And part two, the concavity of the graph must change when x is equal to c. Now, if we know that we have a point of inflection, that tells us two things. Either the second derivative of our function is equal to 0, or the second derivative of our function does not exist. Or to say this another way, if we're trying to find a point of inflection, we start by looking at the places where either the second derivative is 0 or the second derivative does not exist. And then for each one of these, we check, is it a point of inflection? For example, determine the concavity and find the inflection points of the function x cubed minus 3x squared plus 2. So the first thing we need is the second derivative. 6x minus 6. This exists everywhere. So we're only going to be looking for places where the second derivative is equal to 0. The only way that we can get 6x minus 6 is equal to 0 is if we have x equal to 1. If we're on the left of 1, for example, if x is 0, f double prime would be 6 times 0 minus 6. That's negative. So on the left of 1, the second derivative must be 0. That means concave down. On the right of 1, choose any number which is bigger than 1. Let's say we pick x is equal to 2. 6 times 2 minus 6 is a positive number. So on the right of 1, our second derivative must always be positive. So we must be concave up if we're on the right of 1. As the question says, concave down between minus infinity and 1, and concave up between 1 and infinity. The concavity is changing when x is equal to 1, so we have a point of inflection when x is equal to 1. Put f1 into f of 1. That's 1 cubed, 1 minus 3 plus 2. 1 minus 3 plus 2 is 0. So we have the point on the graph 1, 0 where the concavity changes. And I can show you the graph of this function. On the left of 1 is concave down, on the right of 1 is concave up, and the point of inflection is the point where x is 1 and y is equal to 0. Find all of the points of inflection of x to the power 5 over 3. So we differentiate this function 2 times. 10 over 9 cubed root of x. And then we ask, how can this function be equal to 0, or how can this not exist? Well, the second derivative does not exist if x is 0. If x is less than 0, the second derivative is negative. If x is greater than 0, then the second derivative is positive. So that's concave down on the left of 0 and concave up on the right of 0. So we have a point of inflection when x is 0, and putting that into the formula, if x is 0, y is also 0. The graph of the function looks like this. We can see that it's concave down on the left, concave up on the right, and in the middle we have a point of inflection. The point of inflection is where the concavity changes from concave down to concave up. Another example, y is equal to x to the power 4. Differentiate this 2 times, 12x squared. A typo here, this should be y double prime. Now, we can have y double prime equal to 0 at x equal to 0. But the concavity does not change here. It's concave up on the left of 0 and it's concave up on the right of 0. So that means the point 0, 0 is not a point of inflection of x to the power 4. Just because we have the second derivative not existing or second derivative equal to 0, that doesn't necessarily mean that we have a point of inflection. We still need to check to see if the concavity changes. Let y is equal to x to the power 1/3. Differentiate it 2 times. Minus 2 over 9, x to the power minus 5 over 3. And then note that this second derivative does not exist if x is equal to 0. So there's one place where we might have a point of inflection. We might or we might not have a point of inflection at 0, but we know we don't have a point of inflection anywhere else. So we cut our interval at 0, and we're going to look on the left and we're going to look on the right. On the left of 0, first of all, we can calculate y double prime at one value of x and see that that's positive, so y double prime must always be positive here. So the graph is concave up. But if we look on the right of 0, we can calculate y double prime at one value of x. Let's say you want to use x equal to 1. That's negative. So y double prime must always be negative here. The graph is concave down. The concavity is changing. Concave up on the left, concave down on the right. The concavity changes at the point 0, 0. And the graph of this function looks like this. Concave up on the left, concave down on the right, with a point of inflection in the middle. And that brings me to the second derivative test for local extrema. Suppose that the second derivative f is continuous on the open interval from a to b, and let's suppose c is some point between a and b, some number between a and b. If we know that f prime of c is equal to 0, so c is a critical point, and we know that the second derivative is less than 0, so we have a graph which looks like this. There's a critical point, and round about it, it's concave down. Then the theorem tells us that we must have a local maximum at C. Or if we know that we have a f prime of C is equal to 0 and f double prime of C is greater than 0, so 0 derivative at C and concave up close to C, then we must have a local minimum at C. And thirdly, if f prime of C is 0 and f double prime of C are equal to 0, then we don't know. This theorem doesn't tell us. We need to use a different theorem to understand what's going on. For example, let's consider the function x to the power 4 minus 4x cubed plus 10. And we have 6 questions. Find where the local extrema are. Find the intervals where f is increasing and the intervals where f is decreasing. Find the intervals where f is concave up. Find the intervals where f is concave down. Sketch the general shape of the graph y is equal to f of x. Plot some points which satisfy y is equal to f of x, and then graph y is equal to f of x. In other words, draw the graph of y is equal to f of x. Okay, so what can we say? Well, our function is a polynomial, and all polynomials are continuous. They have continuous derivatives. The domain of f is the whole real line. F prime is 4x cubed minus 12x squared, and this is a polynomial. All polynomials are continuous everywhere. So the domain of f prime is also the whole real line. That means there's no points where f prime does not exist. To find the critical points, we just need to solve f prime of x is equal to 0. So we do our calculation. We start with 0 is equal to f prime of x. Factorize this and then see how can we make this 0. this is 0 if x is 0, or this is 0 if x is equal to 3. So we're going to take our domain from minus infinity to infinity, and then we're going to make a cut when x is 0, and we're going to make a cut when x is equal to 3. We're looking at the intervals from minus infinity to 0, from 0 to 3, and from 3 to infinity. On each one of these, we need to decide, is f prime positive or is f prime negative? And that will tell us if f is decreasing or increasing. Now, at 0, it's decreasing on the left and decreasing on the right, so that's not an extremum. At the point 3, it's decreasing on the left and then it's increasing. So that must be a local minimum. We can say that f is decreasing between minus infinity and 0, and between 0 and 3, and we can see that f is increasing between 3 and infinity. For the next part of the questions, we need to find the intervals where it's concave up and concave down. So to answer the next part of the question, we need to solve f double prime is equal to 0. Remember, we have a polynomial. Polynomials are differentiable everywhere, so there will be no points where the second derivative does not exist. We're only looking for the points where the second derivative is equal to 0 in this example. So I start with f double prime is equal to 0. That's 12x squared minus 24x. I must have that x is 0 or x is equal to 2. So we take our whole real line and we cut it at 0 and we cut it at 2. Our open intervals are from minus infinity to 0, from 0 to 2, and from 2 to infinity. And then we're asking, is the second derivative positive or negative on each interval? And after we've found that, we can see that f is concave up between minus infinity and 0, concave down between 0 and 2, and concave up between 2 and infinity. Let's just summarize what we've done so far. The domain of our function is the whole real line. First, we looked at f prime of x is equal to 0, and we found that x is 0 or 2. So we're cutting our domain at 0 and at 2. Is that a typo? I made a mistake here. This should be over here. We cut at 0 and at 3. And then we looked at where the second derivative is equal to 0, and we saw that that was at 0 and at 2. So we're also cutting at 0 and at 2. So that gives us 4 sub-intervals. From minus infinity to 0, from 0 to 2, from 2 to 3, and from 3 to infinity. Let's summarize on what we know on each of these. Between minus infinity and 0, our function is decreasing and concave up. Decreasing and concave up looks like this type of curve. Between 0 and 2, the function was decreasing and concave down. Decreasing and concave down looks something like this. Between 2 and 3, the function was decreasing and concave up. That looks something like this. And then between 3 and infinity, we found that our function is increasing and concave up. Increasing and concave up looks something like this curve. If we take these 4 curves, and if we glue them together, we end up with the general shape of f. The graph of f is going to look something like this. Now, to answer question 5, we can calculate some x, y points. Put x is 0, 2, 3, 4 into the formula, and we can calculate the value of y, and then we can plot these on the axes. We know the shape of the function. We know that the graph looks something like this, and it must pass through these 4 points. With that information, we can sketch the graph of y is equal to x to the power 4 minus 4x cubed plus 10. Let's recap our method. Here's the procedure. Step 1, identify the domain of the function and any symmetries the curve might have. Is it an even function, an odd function, etc. Step 2, find the derivatives, y prime and y double prime. Step 3, find the critical points of f, if it has any, and identify the function's behavior in each one. Step 4, find where the curve is increasing and where it's decreasing. Step 5, find the points of inflection, if any occur, and determine the concavity of the curve. In other words, find the intervals where the graph is concave up and find the intervals where the graph is concave down. Step 6, do we have any asymptotes? Step 7, plot the key points. Intercepts, that's where it crosses the x and y axis, anywhere where we could have an extremum, and then sketch the curve together with any asymptotes that you found. So, for example, I want to sketch the graph of x plus over 1 plus x squared. What do we know about this function? The domain is the whole real line. This function is not even, and this function is not odd. We don't have any symmetries. We need to differentiate this function 2 times. I leave it for you to check that these derivatives are correct. And then I want to look to see where is the first derivative equal to 0 and where is the second derivative equal to 0. Well, the first derivative, which exists everywhere, is equal to 0 if and only if x is plus or minus 1. The second derivative also exists everywhere, and this is equal to 0 if x is 0 or if x is plus or minus the square root of 3. So what we're doing is we're taking the domain of the function, that's the whole real line. We're going to cut where the first derivative is equal to 0, and we're also going to cut where the second derivative is equal to 0. So that's going to give us 6 sub-intervals. Now, looking above, as I've showed you how to do before, we can find that the function is decreasing between minus infinity and minus 1. It's possible to find that the function is increasing between minus 1 and 1, and we can find that it's decreasing between 1 and infinity. Please check that for me. And then in green, it's possible to find that the function is concave down between minus infinity and minus square root of 3. It's concave up between minus the square root of 3 and 0. It's concave down between 0 and root 3, and it's concave up between root 3 and infinity. Let's put all of this information in a table. Here are our 6 subintervals. And on each one of these, we know whether the function is decreasing or increasing, and we know if the function is concave down or concave up. The next idea is about asymptotes. Does this function have any asymptotes? Well, asymptotes is something we've talked about before. Asymptotes is a topic which is covered by the first midterm exam. So hopefully you're familiar with these. For horizontal asymptotes, we calculate the limit as x tends to infinity or the limit as x tends to minus infinity. And using this type of calculation, which we've done before, both of these limits are equal to 1. So that tells us that y is equal to 1 is a horizontal asymptote. Does this function have any vertical asymptotes? No. This function is defined everywhere, so there are no vertical asymptotes. Now we have enough information to sketch the graph. First, I've drawn this horizontal asymptote, y is equal to 1. I'm going to plot some points just by sticking minus root 3, minus 1, 0, 1, and root 3 into the formula. I can calculate the value of the function at these 5 points, and then I can plot these on the axes. We know where the function is increasing, we know where the function is decreasing. We know where the function is concave up, and we know where the function is concave down. So using that information, we can draw the graph like this. First part is decreasing and concave down. The second part we've seen must be decreasing and concave up. And then it's increasing and concave up, and then increasing and concave down. The fifth part we've seen must be decreasing and concave down, and then the final part is decreasing and concave up. And remember, as we go closer and closer to infinity, the graph gets closer and closer to the horizontal asymptote. Where are the points of inflection? Well, here's one. We change here from concave down to concave up. At minus 1, it's concave up, concave up. That's not a point of inflection. At 1, we change from concave up to concave down. At 1, concave down, not a point of inflection. At root 3, concave down changes to concave up. So we have 3 points of inflection. And I think this is a good place to take a 10-minute break. And let's continue. Another drawing the graph example. Sketch the graph of x squared plus 4 divided by 2x. This function is not defined if x is equal to 0 because we can't divide by 0, but it's defined everywhere else. And this function is an odd function. Now, we need to differentiate this 2 times. First derivative is x squared minus 4 over 2x squared, and the second derivative is 4 over x cubed. Looking at the first derivative, we are looking for the points where f prime does not exist or f prime is equal to 0 inside the domain of f. And remember, the domain is everything except x equals 0. If x is not equal to 0, f prime exists. So there's no point in the domain of f where f prime is not equal, where f prime does not exist. So we're only looking for the points where f prime is equal to 0. That can only happen if x squared minus 4 is 0. So the critical points are x is minus 2 and x is 2. So let me just repeat that. X equal to 0 is not a critical point because 0 is not in the domain of f. And we know that there are no points of inflection because f double prime exists everywhere in the domain of f. F double prime is defined everywhere except at x equal to 0, but x equal to 0 is not in the domain of f. So we're not ignoring that. And f double prime is always not equal to 0 where it exists. So we have our domain that's from minus infinity to 0, union 0 to infinity, and we're going to cut this at the critical point. So we're going to cut it at minus 2, and we're going to cut it at 2. That gives us 4 intervals that we need to consider. From minus infinity to minus 2, from minus 2 to 0, from 0 to 2, and 2 to infinity. On each of these intervals, we can ask, is the function increasing or decreasing? Is the function concave up or concave down? And you know how to do this now. We look to see is the first derivative positive or negative, and we look to see if the second derivative is positive or negative. So we have increasing and concave down, and then decreasing and concave down. Then we have decreasing and concave up, and then increasing and concave up. Let's look at the asymptotes of the graph. If we take the one-sided limits at 0, we get either infinity or minus infinity. So that tells us that the line x equal to 0 is a vertical asymptote. If we think of our function as x over 2 plus 2 over x, and because the limit as x tends to infinity or minus infinity of 2 over x is equal to 0, that tells us that our graph is getting closer and closer to y is equal to x over 2 as x gets bigger and bigger. So y equal to x over 2 is an oblique asymptote. So here we are. Here's the asymptotes. There's the vertical asymptote, and here's the oblique asymptote. Let's plot a few points. In fact, let's just plot 2 points. And remember the shape. It was increasing and concave down, and then decreasing and concave down, and then the graph was decreasing and concave up, and then increasing and concave up. Using all of this information, we can sketch the graph of the function. There's another example in your textbook, but I leave that for you to read. When you study this topic, please make sure that you also read example 11. Let's move on to section 4.5, which I'm going to talk about quickly. I'm just going to do some examples. First example, an open top box is to be made by cutting x centimeter by x centimeter squares from the corners of a 30 centimeter by 30 centimeter piece of metal, and then bending the corners up. Sorry, bending the sides up. How large should the squares cut from the corners be to make the box hold as much as possible? So let me just explain that again with a picture. We're starting with a 30 centimeter by 30 centimeter piece of metal, and then we're going to cut squares out from the corners, throw those away, and then we're going to fold up on the dashed lines to make an open top box. The height of this box is going to be x, because the squares we cut out are going to be size x. And the other two dimensions are going to be 30 minus 2x. Because we start with 30, we cut away x on the left, and we cut away x on the right. Now, we're expecting the volume of this box as a function of x to look like this. If x is 0, then we just have a flat piece of metal. So if x is 0, of course, the volume is 0. And if x is 15, then of course we're cutting all of the metal away. So again, we would end up with a volume of 0. And then in the middle, it's going to go up, and then it's going to come down. And somewhere between 0 and 15, we would have our maximum. And this is what we're trying to find. What value of x should we choose if we want our box to hold as much as possible? So we start with a formula for the volume of a box. That's easy. X multiplied by 30 minus 2x multiplied by 30 minus 2x. And x must be between 0 and 15. We can't cut out more than 15 centimeters, and we can't cut a negative amount of centimeters away. We want to look for the point where the derivative of f is equal to 0. So we're looking for critical points of v. So we differentiate v, and we find our formula. The derivative of v is 12 multiplied by 15 minus x multiplied by 5 minus x. And this is equal to 0 if x is 5 or if x is 15. Go back to the graph. This point where the slope is equal to 0 is either 5 or it's 15. Well, we can look at the graph and we say it can't be 15, so it must be 5. Or in terms of just using the equation, because 15 is not an interior point of our domain, the only critical point is x is equal to 5. So to get the largest possible box, we want to choose x is equal to 5. And if we choose x is 5 centimeters, then our box will have a volume of 2 liters. So this is the idea. We're going to be finding a value of some variable, in this case x, which finds a maximum or finds a minimum of our function. Let's do another example. You're designing a 1 liter cylindrical drinks can. So this is a different type of question because we're told that the volume must be 1 liter. You will use the same metal and the same thickness of metal for the top, bottom, and sides. And we're going to make this in the shape of a cylinder. So really we're making a cylinder with volume 1 liter. What dimensions will use the least amount of metal? Well, that's the same as saying which dimensions, which R and which H, will have the least amount of surface area. To answer this question, we're going to use centimeters. We're going to say that the radius of the can is R centimeters and the height of the can is H centimeters. So how do we make a cylinder? We need 2 circles and we need a rectangle. These circles are going to be circles of radius R. For the sides, the height is going to be H, the height of the cylinder, and the width of this rectangle is going to be the same as the circumference of each of these circles. The circumference of a circle of radius R is 2 pi R. What can we say? The volume is 1 liter or 1,000 cubic centimeters, and the volume of a cube of radius R and height H is pi R squared. That's the area of the top and the bottom multiplied by the height H. And the surface area of the can, well, we have pi R squared for the top, pi R squared for the bottom, so 2 pi R squared, and then for the sides, 2 pi R multiplied by H. The volume is fixed at 1 liter. We want to make the surface area of the can A as small as we can. Now we've got 2 variables here. We've got R and we've got H, but we need to remove one of these, and we're going to remove these using what we know. We know that pi R squared H must be 1,000. If we rearrange that, H must be 1,000 over pi R squared, and then we're going to put that into the area formula. As a function of R, the surface area must be 2 pi R squared plus 2,000 divided by R. And the graph of A looks like this. If R is a small number, in other words, if we have a tall and narrow can, then the area is going to be quite high. If R is a big number, if we have a short and wide can, then again, the area will be quite big. Somewhere in the middle, there's going to be a minimum. How do we find the minimum? We're going to look for the critical points of A. Because at the minimum, we're going to have that A prime is equal to 0. So we want dA, dr, that should be. We want dA, dr is equal to 0. So differentiate A, rearrange, and we find that R must be the cubic root of 500 over pi, which is approximately 5.42 centimeters. And then after we know R, we can use the previous equation to find h. Previously, we saw that h must be 1000 divided by pi r squared. Substituting r as cube root of 500 over pi and rearrange, we end up with approximately 10.84 centimeters. These are the dimensions which will have the least surface area, so we'll use the least amount of metal. And I have one more example. A rectangle is to be inscribed or drawn inside a semicircle of radius 2 as shown in this diagram. What is the largest possible area of the rectangle? So what can we say? The equation for a circle of radius 2 is x squared plus y squared is equal to 2 squared. We're going to imagine that this corner of the rectangle is at the point xy, where xy must solve the formula for the circle. So then this distance must be x, and therefore the width of the rectangle must be 2x, and the height of the rectangle must be y. So the area of this rectangle must be 2xy, where x and y satisfy the equation x squared plus y squared is equal to 4. So our area is 2xy, and xy must satisfy x squared plus y squared is equal to 4. In other words, y is the square root of 4 minus x squared. Put this into the area formula. The area of the rectangle must be 2x square root of 4 minus x squared. We want to find the maximum of this function. So what we do is we differentiate it. If we differentiate a, we get this formula, and we want this to be equal to 0. So we need to rearrange this. We can do that by multiplying by the square root of 4 minus x squared, and we end up with 0 is equal to 4, 2 minus x squared. So x must be plus the square root of 2 or minus the square root of 2. But in our picture, we were assuming that x was between 0 and 2. So we must have that x is the square root of 2. And as soon as we know that, we can calculate the maximum possible area. That's a root 2. Put that everything into the formula, we end up with our answer 4. Now, all three of these examples were basically the same. We're all trying to find the maximum, or we're trying to find the minimum of some function. In your textbook, there's 3 more examples, and the idea is always the same. It's always we're getting some sort of function, and then we're trying to find the maximum of it, or we're trying to find the minimum of it. So I'm going to leave these last 3 examples for you to read. Instead, I want to move on to our final topic for today's lesson, antiderivatives. What is an antiderivative? A function capital F is an antiderivative of small f on an interval I if and only if capital F prime is equal to small f on this interval. So, for example, we know that 2x is the derivative of x squared. Turn that around, swap the positions of x squared and 2x. X squared is an antiderivative of 2x. So we're just doing derivatives, but we're going backwards. Sine x is an antiderivative of cos x because if we differentiate sine, we get cos. And we could add these together. X squared plus sine x is an antiderivative of 2x plus cos x, because if we differentiate x squared plus sine x, we get 2x plus cos x. Antiderivatives, you can think of doing differentiation backwards. But let me remark that x squared is not the only antiderivative of 2x. X squared plus 1 is an antiderivative of 2x, because if we differentiate x squared plus 1, we get 2x. And x squared plus 5 is an antiderivative of 2x, because the derivative of x squared plus 5 is also 2x. Or x squared minus 1234 is an antiderivative of 2x, because the derivative of x squared minus 1234 is 2x. What's the difference here? It's always x squared first, but then we're doing plus or number. Theorem: if capital F is an antiderivative of f on I, then the general antiderivative of f is capital F plus c. In other words, every antiderivative of small f is of the form capital F plus some number c. For example, find an antiderivative of 3x squared that satisfies f of 1 is equal to minus 1. We need to find a function capital F which satisfies two things. If we differentiate capital F, we get 3x squared. And if we calculate capital F at 1, we get the number minus 1. Well, first of all, we can say that x3 is an antiderivative of f because the derivative of x3 is 3x squared. So we take out x3, x cubed, and we add on a constant. And that gives us the general antiderivative of small f. We've satisfied the first condition, but we also need to satisfy that capital F of 1 is equal to minus 1. We need to choose the value of the constants so that we have f of 1 is equal to minus 1. So this is what we want. We want minus 1 is equal to capital F of 1. And we know that capital F of x is x cubed plus c. So capital F of 1 must be x cubed plus c, or 1 plus c. We need to choose the number c so that 1 plus c is equal to minus 1. Well, that's straightforward. If c is minus 2, then 1 plus c is the same as minus 1. So this is the one we want. We want minus 2 just here. The answer to this question is x cubed minus. Let me just recap a few of the derivatives we've seen so far. The derivative of x to the power n we've seen is nx to the power n minus 1. The derivative of sine kx is x cos kx. The derivative of cos kx is minus k sine kx, and the derivative of tan kx is k sec squared kx. Now let's talk about antiderivatives. First of all, x to the power n, as long as n is not equal to minus 1. Well, what do we do if we differentiate this? If we differentiate it, we decrease the power by 1, and then we multiply it by n. What is the opposite of this? The opposite of decreasing the power is increasing the power. And the opposite of multiplying by a number is dividing by a number. The general antiderivative of x to the power n is x to the power n plus 1 divided by n plus 1 plus c. Let's just check this very quickly. What do we get if we differentiate x to the power n plus 1 over n plus 1 plus c? Well, if we differentiate x to the power n plus 1, we decrease the power by 1 to x to the power n, and then we multiply it by n plus 1. And of course, the derivative of c is 0. n plus 1 cancels with n plus 1, and we just end up with x to the power n. Next, let's look at cos. Well, if we differentiate sine, we get cos. So going the opposite way, an antiderivative of cos must be sine. When we differentiate, we multiply by k. The opposite of that is dividing by k, or multiplying by 1 over k. So the general antiderivative of cos kx is 1 over k sine kx plus c. If we differentiate cos, we get minus sine. So the opposite of that is the antiderivative, the general antiderivative of sine must be minus cos. And again, if we differentiate, we multiply by k. So when we do an antiderivative, we divide by k. And then the bottom line of this table, the derivative of tan is sec squared, so an antiderivative of sec squared must be tan. The general antiderivative of sec squared kx is 1 over k, tan kx plus c. Example 3 from your textbook, find the general antiderivative of each of the following functions. X to the power 5, 1 over root x, sine 2x, and cos x over 2. Let's look at A first of all. We increase the power from 5 to 6, and then we divide by 6, x to the power 6 over 6, and then we do plus c. When we're doing general antiderivatives, don't forget that you have to do plus c. B, we have the function x to the power minus a half. So we do the same thing. We increase the power by 1, minus a half becomes plus a half, and then we divide by the new power. So x to the power half divided by a half plus c. Or 2 root x plus c. And we can check that this is correct by differentiating this. If we differentiate 2 root x plus c, you can check that we get 1 over root x. General antiderivative of sine 2x, well, we talked about that on the table on the previous slide. Derivative of cos is minus sine, so antiderivative of sine must be minus cos. If we differentiate, we're going to be multiplying by 2, so we do the opposite now. We divide by 2. minus cos 2x over 2 plus c. And then part D, I'll leave for you to read when you read your textbook. We had a sum rule and a constant multiple rule for derivatives. We also have one for antiderivatives. Suppose that capital F is an antiderivative of small f, capital G is an antiderivative of small g, and k is a number. The sum rule is that the general antiderivative of f plus g is capital F plus capital G plus c. Don't forget the plus c when you're doing general antiderivatives. And the constant multiple rule, the general antiderivative of kf is k capital F plus c. For example, find the general antiderivative of 3 over root x plus sine 2x. We have 3 times a function plus a function. Where our first function is x to the power minus a half, we know it an antiderivative of that, and our second function is sine 2x. We know an antiderivative of that. An antiderivative of x to the power minus a half is 2 root x. An antiderivative of sine 2x is minus a half cos 2x. So the general antiderivative of f, take capital G and multiply it by 3 to get 6 root x plus h minus a half cos 2x, and then at the end we do plus c. You drop a box off the top of a tall building. The acceleration due to gravity is 9.8 meters per second squared. You can ignore air resistance. How far does the box fall in 5 seconds? So here we are. This is my picture of you. You're standing on the top of a tall building and you're going to drop a box off the building. And then the box is going to fall straight down. We're going to say v is the velocity of the box. And we're going to say s of t is how far the box has fallen in t seconds. We're told that the acceleration is 9.8 meters per second squared downwards. And because acceleration is the derivative of velocity, that means that velocity is an antiderivative of the acceleration. So the velocity must be 9.8 t plus c meters per second. But wait a minute, the question said that you let go of the box at time, you drop the box. So at time t equal to 0, it's when you let go of the box, the velocity at time 0 is 0. So if we have 0 is equal to 0 plus c, that tells us that c must be 0. So the velocity of the box must be 9.8 t meters per second. But velocity is the derivative of displacement, or to say it again, say it the other way around, distance fallen is an antiderivative of velocity. So the distance the box has fallen must be 4.9 t squared plus some constant meters. Again, at time t equal to 0, you're holding the box and you let go of it. So that means at time t equal to 0, the box has fallen 0 meters. So we have displacement is equal to 4.9 multiplied by 0 plus this new constant. So this constant must be 0 as well. And we have that the box falls 4.9 t squared meters in t seconds. We were asked how far does the box fallen after 5 seconds? The answer is 4.9 multiplied by 25, or 122.5 meters. We've been talking about general antiderivatives. I've been using the phrase general antiderivative, but there's another name for the same thing. The general antiderivative f is also called the indefinite integral of f with respect to x. And we write it like this. We have this stretched letter s, f of x dx. This stretched letter s is called the integral sign. The function that we're trying to find the general antiderivative, or the indefinite integral of, is called the integrand. And the dx on the end tells us that x is the variable of integration. So, for example, the indefinite integral of 2x, or the general antiderivative of 2x, is x squared plus c. The indefinite integral of cos x dx, that's the general antiderivative of cos x, is sine x plus c. And then add them together, the indefinite integral, or the general antiderivative of 2x plus cos x, is x squared plus sine x plus c. For example, calculate the indefinite integral of x squared minus 2x plus 5 dx. I'm going to solve this two ways. Let's suppose that we can see an antiderivative straight away. Let's suppose we've been doing calculus long enough that straight away we can look at x squared minus 2x plus 5 and we can say, I know an antiderivative of that is x cubed over 3 minus x squared plus 5x. Then the answer to this question is this function, and then always remember plus c. Or let's solve this another way. What we can do using the sum rule is we can split this up into 3 easier indefinite integrals. The indefinite integral of x squared minus the indefinite integral of 2x plus the indefinite integral of 5. And for each one of these, we can write down its value. We can find the general antiderivative of each integrand. For the first one, we have x cubed over 3 plus c1. For the second one, the general antiderivative of 2x is x squared plus c2. And for the last one, the general antiderivative of 5 is 5x plus c. So again, we have the same function as before, x cubed over 3 minus x squared plus 5x, plus some constants. Now, c1, c2, and c3, they're all numbers that we don't know. We only need one constant here. So we can replace these 3 numbers that we don't know by a new name. Let's introduce a new constant c, which is c1 minus c2 plus c3. And then the answer to this question is x cubed over 3 x squared plus 5x plus c. In this example, I've tried to show that we only need one constant. We don't need to worry about different constants. We only need to have one. And that's the end of this week's lesson. Next week, I'm going to start talking about chapter 5. I'm going to cover sections 5.1, 5.2, and 5.3. Are there any questions?